Okay, this is going to be the final part of this run-through for this June 2023 exam, which I have already uploaded the multiple choice questions on thermodynamics in separate parts, questions on nuclear physics in a separate part, and questions on simple harmonic motion and oscillations in a separate part. There's 2 questions remaining. So we've been through the thermodynamics questions. We've been through the nuclear questions, which they call radiation. Yes. We've been through the oscillations. So in this video, I'm going to go to the final 2 questions, which are on cosmology. Yeah. So if you haven't watched the previous videos, you may want to go and watch them first. Don't forget to like and share the video with anyone who you think will benefit from this Pearson Edexcel International A-Level. So it's for physics, Unit 5, which is the final content of Year 13, which matches the Edexcel Linear Advanced 2 content. So Advanced Paper 2 in Linear covers these topics as well, plus Year 12 topics, yeah, which you will be aware of. So because there aren't enough linear advanced papers, because there's only 1 exam per year, my recommendation is for you to go and use the modular to prepare a deeper knowledge of these topics before using your own papers as your final practice. Okay, so we went through question 11 and 12. Question 12 was thermodynamics. We went through question 13, which was on ionization energies. We calculated specific capacity and latent heat in the thermodynamics questions here, and this is a question on nuclear fusion. So this is a good link with what we're going to do now, because we're talking about energies for fusion, which is what fuels star nuclear processes. Okay, so this is question 17. If you haven't been through it, you'll see the thermodynamics and nuclear fusion are closely related. Okay. You need high temperatures. We also went through binding energy per nucleon, yeah, which is a very important part of understanding what happens. And in fact, all of these nuclei were made in stars. So the stars are the nuclear factories of the universe. So every atom that's on Earth now was once made inside a star, which is no longer fusing, yeah. All right, so we've done 18, we've done 19, which was simple harmonic motion, which was to do with springs, and here is one of the final questions, which is to do with the Hertzsprung-Russell diagram for a star cluster as shown. Now, when I did my astrophysics degree way back, and I'm talking about way back, this was taught at university. This was not covered in school. So you have a broader A-level than I had. Mine was more mathematical, and there's certain areas which are no longer in A-level. So, but the A-level now is broader, and I would say slightly less deep, okay, mathematically at least. So you've got luminosity on the y-axis, and you've got temperature in Kelvin on the x-axis. You'll notice that neither of these axes are linear. You can see it goes from 3,000, then doubles to 6,000, then 12,000, and therefore the next one should be about 24,000. And you can see the y-axis also is not a linear scale. And the reason they do that is because there's a big range in luminosity of stars. So our sun is around here because the luminosity 1 represents the star, our sun. So all the other luminosities are how many times they are compared to the sun. Okay, so below 1 are less luminous, and above this 1 are more luminous. So this would be 100 times more luminous, yeah, and 1,000,000 times more luminous, 10 to the 6. And luminosity is measured in watts. Okay. So I hope that's a good intro. So you can see where the main sequence stars are. That's what the ones that are fusing hydrogen in the main part of their life. They are younger than the older red giants because when they run out of hydrogen fusion, yeah, they go into the red giant phase and they're older. and depending on their mass, they will have a different luminosity. You can see that also their surface temperature, the temperature we're talking about, is the surface temperature, not the internal temperature. And from the surface temperature, if you remember from GCSE, we can tell from the colour and the surface temperature are linked. And then white dwarfs are what happens to stars like our sun when they run out of all the fuel that they can fuse, whether it's in the main sequence stage or in the red giant phase. Okay, they become white dwarfs. So the first thing they want you to do is add a scale to the horizontal axis. So you can see that I've already done it and I've already explained it to you. So if you get the temperatures in the right place and you realize that it's not linear, and you can see the temperatures increase going inwards, which is unusual compared to most other graphs you've met. It then wants you to explain how. This diagram, called the HR diagram, or Hertzsprung-Russell, okay, shows that the star cluster is not a young star cluster. Well, it's not a young star cluster because it's already got red giants and white dwarfs on it. You should refer to the groups of stars and their positions on this diagram, which I've already referred to in my introduction. A young cluster of stars would have only or mostly main sequence stars or protostars, perhaps. Yes, no, protostars have not really been shown on this diagram. Protostars are before they reach the critical temperature for fusion to occur in the interior. This cluster has many red giant stars, top right of the diagram as I've drawn them, as I've labeled them, and red giant stars evolve from main sequence stars once they run out of hydrogen fusion. Okay, so the hydrogen is being used up to an extent where they can no longer fuse hydrogen together, so they've got to look to possibly fuse helium and, for some stars, larger nuclei. This cluster also shows some white dwarf stars, which are even older. Yeah, they are the end of the life cycle of stars' evolution, and they could say they are dying stars, and they're in the bottom left of the diagram. So I think those 3 bullet points will be sufficient for you to get the 3 marks to satisfy the examiner in terms of answering the question. That we can see it's not a young cluster of stars because they have a variety of aging stars in there. Okay, so reverse scale for the x-axis, we've done that, approximately logarithmic, that means you're doubling or going up with realistic values of temperature, especially for the sun around 6,000 Kelvin. You need to know that. Okay, so the star is not a young cluster because the star has red giant stars. It has white dwarf stars, yes, and the young cluster would only have main sequence stars. So basically that's, in a nutshell, the 3 marks they're looking for. In the next part of the question, we're going to talk about standard candles, which have known luminosities, and how we can use the known luminosity of standard candles by measuring their intensity from Earth and then determine their distance using this equation of intensity, which we did in year 12. Yeah, so this was in 12 AS, and that's in waves. So the intensity of radiation is equal to the luminosity divided by its distance squared. And of course, 4 pi d squared is in reference to the fact that when it goes a distance, you have a sphere that is radiating out over, and this is the surface area of a sphere is 4 pi r squared. So basically, the further away it is, the dimmer it will appear. And here they put d instead of r because it's the distance that we want to do. But it's basically a sphere of surface area 4 pi r squared where all of the luminosity is now spread out over. And that's what the inverse square law is. Okay? Question 21 is also going to be on cosmology, where they're going to talk about Wien's law, or W-I-E-N-S, Wien's law, which allows us to analyze the radiation emitted by a star and to work out its temperature as a result, okay, because there's a known equation for that. If you've done your revision, you'll know. And again, they're using an area of 4 pi r squared. Again, they're using luminosity. This is the Stefan Boltzmann law. and you can then use these equations to solve problems. So we're going to also, in question 21, use the luminosity concept. Okay, but for this part C, which is to do with luminosity and distance, in the early 20th century, it says Hubble observed the Andromeda Nebula. Okay, a nebula is a mass of gas, or what appears to be a mass of gas. He saw stars similar to the stars in our galaxy. One star he saw was classified as a standard candle. That means known luminosity. Known luminosity, L for short. Okay? Describe how measurements of this standard candle could demonstrate that the Andromeda Nebula is not in our nearby stars. Now remember, to do this, you need to talk about what standard candles are. So you need to show that you know what a standard candle is, so it has a known luminosity. You then need to measure the intensity from where you are, which is then I equals L over 4 pi r squared. Yeah, or you could do d for distance. And once you've measured the intensity, we know the intensity, and the standard candle, we know the luminosity. You can then calculate the distance, which will be r. And then if the distance is too large, if it's too large, it will be, so you've got to put too large. So the distance is too large. Let's even change that to, I know I'm writing in note form. One student who was watching my GCSE videos said, you need to write in full sentences. And I said, no, you need to write in full sentences. I need to explain it to you. So my videos are not there to give you exactly correctly worded phrases. I'm doing that in audio for the sake of clarity. Your job is then to go and make model answers having listened to my audio. If distances are too large, then it can't be in our galaxy. So we kind of know, and I think these are the 4 points. We kind of know the size of our galaxy, so once we measure these two, yeah, well, you measure I, and you know L, you can work out R. Okay, so that's the calculation of the distance, would be this. And once you know what our size of our galaxy is, you can work out if it's not a nearby cluster, in other words. Okay? All right, let's see if I've got all the mark scheme. So we've got to look at the mark scheme, is what I've said. So I write notes for myself so I don't forget what I'm doing, because I did this paper last year, and I never uploaded it until someone wanted it this year. They said I haven't uploaded it. Okay, so first mark, as I said, the luminosity of a standard candle is known. 1 mark. Measure the intensity of the radiation from this standard candle. Yes, they mean at Earth, at your position. Yeah. Even the mark scheme don't give you the exact phraseology. You've got to do that in the exam, and they will assess you based on the clarity, depth and detail of your answers. Then use the inverse square law to calculate the distance to the cluster. Yeah, because we know I, we measured it, and L is known. Okay, then if the distance is too large for it to be a nearby cluster, you must have the idea that being too far away rather than just being far away. Actually, they haven't mentioned our galaxy. Okay. Yes, they haven't mentioned our galaxy, so I probably was assuming they meant that it's outside our galaxy. So basically, you know the distance, so you kind of just, based on your knowledge of size of our galaxy. So as long as you are explaining that you know that it's too far away, that's going to get you the 4th mark. Okay? So that's probably the most tricky one. All right, so 20 is done. 21 we're coming to now, and that's the final exam question. All right, So remember, if you find it useful, don't forget to share it with your classmates, because the more subscribers I get, the more likely I am to continue to do this, because it is a lot of work. I mainly do them for my own students, and then if I have time, I upload them for you guys, okay, and for my students. So here you got a Ross 154, which is a star, one of the closest stars to our sun, it says, never heard of it. The graph shows the power radiated, basically it's the spectrum of Ross 154, how it depends on the wavelength. So these graphs are common. You put the wavelength on the x-axis, they've done it in nanometers, yes, and you see where the peak wavelength is. The maximum wavelength is here. And this tells us, this allows us to work out the temperature of the star. Because obviously the hotter the object, the shorter the wavelengths will be, because higher energy is shorter wavelengths because of E equals HF, as you know from previous studies. Okay? So once you know that a hotter star will move to the left, the peak wavelength will move to the left. So basically they've analyzed the radiation coming off at each wavelength, and this is the common shape that they create when you analyze the spectrum. Okay? So this is linked to Wien's law, and Wien's law is given on your formula sheet as the peak wavelength multiplied by the temperature in Kelvin will always give you this value, okay, in meter Kelvin. It's not millikelvin, it's meters times Kelvin. Meter for the wavelength and Kelvin for the temperature, okay? So if you want to work out the temperature, and we know the constant, and we know the peak wavelength that we can read from the graph, yes, so I've read it as 850, so I got the 850 from here and put it into there. So once I've done that, I can work out approximately the temperature, so about 3,400, yeah, so it's close to 3,000, which is what they asked us to show. Okay, remember, show that questions means you've got to prove it mathematically. Yeah, is about 3,000 Kelvin, so we have done that. So always refer back to the question at the end to show the examiner that you are thinking. All right, so Wien's law is a very common question. You probably come up in most exams, so you need to know what it is. Part 2, it says the website states that the luminosity of this star is less than 0.5% the luminosity of the sun. Okay? All right, well, we know the luminosity of the sun because it's our closest star and we've measured it. Okay? Evaluate whether this statement is correct. So evaluate whether the statement is correct. It means another show that. Show that the luminosity of this Ross star is less than 0.05 of the luminosity of the sun. Well, we know the 0.05 of the luminosity of the sun will be this. Okay, multiplied by 0.05, so that you need to do. And they've given you another piece of information, which is the radius of the star, okay, in standard form. So now you've got to use this equation, luminosity equals sigma, which is a constant, and the constant is given to you on the data sheet. Here it is, okay. It's the Stefan Boltzmann law, okay, so that's what you've got to look for. Stefan, don't know how many F's there are. I think Boltzmann also has 2 A's on the end. Stefan Boltzmann law. So this is the equation we're looking at. The temperature we worked out in part 1. We need to use that. So remember, it's temperature to the power of 4, don't forget. Okay, and A equals 4 pi r squared, where for the luminosity of the sun, you would use the radius of the star because it's the luminosity at the surface of the star. So you put that value into this equation and it comes up with 4 pi times that radius to the power of 2. Okay? And once you do that, multiply by 3,400. The examiner has rounded up to 3,400, so I'm doing the same. So you can see that the luminosity of Ross, this star, is 1.33 times 10 to the 24 watts per square meter. Okay? Actually, it should be watts. It should be watts. Let's have a look at the mark scheme. because luminosity is in watts, intensity is watts per meter. So is it me that's made a mistake, or is it the examiner? Check mark scheme. So luminosity is in watts and intensity is watts per square meter. So then you are dividing the luminosity of Ross that we calculated by the luminosity of the sun, which is provided here. You put them in there and see what the ratio is. It comes to 0.0346 or 0.35%, which is less than 0.5%. So website is correct. It is less than 0.5%. All right, let me just go back and look at the mark scheme before we look at the next part. Was it here? Yes, it's my mistake. It should be in watts. Yeah? Luminosity should be in watts. Good thing I noticed. I don't like it going out there without me correcting it. So where's my correction? It's here. Watts. Okay? Is the unit of luminosity. Okay? My apologies for not noticing it before. All right, part B, the final part of this exam is 3 marks. And the scientists have observed an Earth-type planet in orbit around this star. Okay, the radius of the orbit is 0.096 astronomical units, which 1 astronomical unit is the distance from Earth to the Sun. Okay, so that's the orbit radius. Calculate the time for this planet to make 1 orbit of its star. Okay, so we want to find T for this planet around Ross. So as I told you, 1 astronomical unit is the distance from our Sun to Earth, which is 150 million kilometers roughly. Okay, that's what it comes up to in meters. And the mass of Ross is given to us because we'll need to work that out. So if we are having orbiting its circular motion, which is in further mechanics from year 13, you can equate the centripetal equation mr omega squared with gmm over r squared. Okay, so both of these are forces which cause the rotation of the galaxy, the orbital radius. So you can see the masses cancel out. So you don't need to know the mass. And the omega squared can then be worked out first, and therefore omega will be equal to this equation if you get rid of the small mass. Okay, so once you know big G is given to you in the data sheet. So this is in your data sheet. This is the universal gravitational constant, G. The mass of the star is given to you in the equation, in the data here. And you divide it by its radius squared, and they told us that it's orbiting at 0.096 of the Earth's distance to the Earth's star. And you've got to cube it, yeah, and you come up with the angular velocity of 2.75 times 10 to the minus 6 radians per second. And you want to find periods, so you can use this equation to change it to make t the subject. So you basically divide 2 pi by what you just worked out, and you get the period as being 2.29 times 10 to the 6 seconds. All right. Now, if you wanted to, you could work it out in how many days that was, but they haven't asked for it, so I haven't done it. And there's your final 11 marks towards your 90 mark total. I hope you found these videos useful. Once again, please show your appreciation each time you watch a video. Do hit the like button, share it with anyone who's doing Edexcel linear or modular. Both of them should be helpful to preparing for your exams coming up in the next week. So Unit 4 is the next exam, which is within the next 7 days. I think it's on Thursday. So we've got about 5 days to prepare for that. I'm not doing any more Unit 4 exams. They're already uploaded on the playlist, so you can go and look at all the Unit 4 playlists that already exist. And then Unit 5 is June the 4th, so I've added quite a few now, so I don't know how many more I'll have time to do, because I'm also preparing students for the linear exam. So if you're doing linear or you're doing modular, thank you for subscribing to the channel, and hopefully see you in the next video. Bye for now.